All right, this is a video on the Pythagorean theorem as well as the converse of the Pythagorean theorem, and we'll take this video in two parts. First, we'll look at the typical traditional Pythagorean theorem and start with an introduction, do a few solved examples, and then we'll explore the converse of the Pythagorean theorem in the second part. So the Pythagorean theorem says this: if we know that we have a right triangle, in other words, we have a triangle with one right angle, then we can conclude that a squared plus b squared equals c squared. A and b represent the lengths of the legs of the right triangle, the two sides that meet at the right angle, and c represents the length of the hypotenuse of the right angle. And I'll spell that out for you here. The hypotenuse of the right triangle is the side of the right triangle across from the right angle, and it's the longest side in the right triangle. Okay, so a squared plus b squared equals c squared is the Pythagorean theorem. Let's do an example where we're trying to find the hypotenuse. And again, we need to know that we're working with a right triangle, and here we are. It's labeled as a right angle there. So we can write out the Pythagorean theorem, and we can say 16 squared plus 12 squared equals c squared. Okay, we're trying to find c, we're trying to find the hypotenuse. 256 plus 144 is c squared, meaning that 400 is equal to c squared. Okay, so the square of the hypotenuse is equal to 400. We'll solve for c by square rooting both sides, and we're going to get c is equal to 20. Okay, so that would be the length of the hypotenuse for that triangle, 20 units. You don't always get a nice whole rational or integer answer when you do the Pythagorean theorem. Sometimes you have to do a little bit of rounding, you'll get a decimal. And in this example, we're going to round to 2 decimal places. The other thing to notice here in this example here on the left, we are looking for one of the legs of the triangle, and we are given the hypotenuse and the other leg of the triangle. So we're going to set up the Pythagorean theorem like so. We're going to say x squared plus 7 squared equals 15 squared. Okay, a very common mistake here would be to say that 15 squared plus 7 squared is x squared, but that would give you that would solve for x if x were the hypotenuse, but here 15 is the hypotenuse. So let's go ahead and solve. X squared plus 49 equals 225. We'll subtract 49 from both sides, and we have x squared equals 176. And if we square root both sides, we get x is approximately 13.266499. And we're being asked to round to 2 decimal places. So I would take those 2 decimal places, and then we would need to realize we would need to round that 6 up to a 7. 13.27 is our rounded solution to that problem. That's the length of that leg of that triangle. On this second problem here, we're looking for an exact answer, which probably means we're either going to get an integer or a rational number, or perhaps we're going to need to simplify some square roots and not do the square roots on our calculator, but keep them as square roots. So let's go ahead and get that set up. Looks like we have an isosceles triangle. We have the sides labeled as being congruent, so we know that this is x over here on the other side, not x squared, just x. And we can write out the Pythagorean theorem. We can say x squared plus x squared equals 12 squared, meaning that 2x squared is 12 squared. So x squared is half of 12 squared. 12 squared is 144, so let's chop that in half, and we'll get a 72. Okay, we're going to work on simplifying this square root, and to do so we need to think about factors of 72 that are perfect squares. And the largest perfect square that's a factor of 72 is going to make this the easiest to work with. So 36 is a perfect square that's a factor of 72. So we can say that x is the square root of 72, which means that x is the square root of the product of 36 and 2. And I chose 36 again because 36 is the largest perfect square that goes into 72 evenly. We can split that square root apart and call that the square root of 36 times the square root of 2. And we chose 36 being a perfect square as its square root is 6. And that would be our solution right there. X is equal to 6 times the square root of 2. We don't want to take the square root of 2 and get a decimal for it. That would lead to some rounding, a decimal approximation. We're looking for an exact answer here. So 6 root 2 would be our answer. We can also do the Pythagorean theorem for finding distance. And you know, you've probably been taught something called the distance formula, which is basically the Pythagorean theorem when we're working with coordinate geometry on a graph. And you could certainly use the distance formula. I like to just draw a picture or visualize the problem I'm working with and then draw a triangle from there and use the Pythagorean theorem. So let's plot these points over 3 up 6. So that's 3 comma 6, and negative 2 comma negative 1 would be right there. So we're looking for the distance between those 2 points. I can tell that that's going to be the hypotenuse of a right triangle, so I can draw in the right triangle here. And then I can just find the lengths of those legs. This is going to be 7, and this is going to be 5. And x is what we're looking for. So we can say 5 squared plus 7 squared is x squared, meaning that 25 plus 49 is x squared. So x squared is 74. Let's square root both sides. And I'm going to do some rounding. I'll round to the nearest hundredths place. X is 8.60. A couple things you always want to check when you're doing the Pythagorean theorem. After you have all the sides figured out, make sure the hypotenuse is longer than either of the 2 legs. And here it is. 8.6 is certainly longer than 7 or 5. The converse of the Pythagorean theorem means that our given information and what we can conclude are swapped. Okay, you can see this arrow running in the opposite direction. So in this case, if we know that a squared plus b squared is c squared, then we can conclude that we're working with a right triangle. So in this sort of a situation, you're often given the sides, the 3 sides of a triangle, and then you can conclude if the triangle is a right triangle or not. So let's do these couple problems here. So we're being asked, is this a right triangle? So we're going to check using the Pythagorean theorem. First, it's good to highlight whatever the potential hypotenuse might be, okay? If it is a right triangle, the hypotenuse would certainly be the largest side. So that's what we want to set up as C in the Pythagorean theorem test we're doing. So 10 squared plus 24 squared, is that equal to 26 squared? We're just going to run those into our calculator and see what we get. So is 100 plus 576, is that equal to 676? And it is. Yes, we're working with a right triangle. So we can conclude that we're working with a right triangle for that first one. Let's look at the next one. We're testing, is 9 squared plus 16 squared, is that equal to 21 squared? Okay, so is 81 plus 256, is that equal to 441? I can even do a little bit of arithmetic in my head. A 1 plus a 6 yields a 7, and we don't have a 7 right there. So I can tell already that we're not dealing with a right triangle, but let's finish the problem. 337 is definitely not equal to 441, so we can conclude that we do not have a right triangle here. All right, you can do a little bit more with this sort of a problem and not just determine whether or not you're working with a right triangle. You can determine whether or not the triangle is obtuse or acute. And I have kind of a visual, intuitive way of thinking about this. If we're working with an obtuse triangle, in other words, if the angle between A and B is obtuse, it kind of means that C has been pushed out too far, that angle has been opened up too much, and C is longer than you would expect it to be if the Pythagorean theorem was working. And separately, for an acute triangle, you can think of C as being sort of too small, smaller than the Pythagorean theorem would suggest, and then we would have an acute triangle. So a way that you can write this out is here, C is greater than A squared plus B squared. Excuse me, C squared is greater than A squared plus B squared, okay? because the triangle has been pushed apart sort of too much. And for an acute triangle, you can say c squared is less than a squared plus b squared. Okay, I don't really remember those inequalities. I just remember thinking about visually if that triangle has been sort of pushed apart or pulled together. So our last example for this video will actually be to apply this, and we have a triangle with 3 sides, 6, 11, and 14, and we're curious. We're wondering, is this a right triangle? And if it's not, is it acute or is it obtuse? Okay, and we're going to assume the 14 will take the place of the hypotenuse. Okay, so let's see what the hypotenuse should be if it were a right triangle. So I'm going to ignore the 14 for now, and I'm going to say 6 squared plus 11 squared equals c squared. And let's solve for what the hypotenuse should be. We get 36 plus 121 is c squared. So that's 157 equals c squared. We'll square root both sides. And we get c is roughly equal to 12.53. Okay, so I'm going to draw a quick picture here, and I know I haven't even used the 14 yet, but we'll get there. So if we have a triangle that looks roughly like this, and if it were to be a right triangle with legs of 6 and 11, we would have a hypotenuse of 12.53. This hypotenuse, or not the hypotenuse, but this third side of the triangle we're given here is 14. It's too long, it's too big. Okay, so 14 squared is larger than our 6 squared plus 11 squared. And so therefore we can conclude that the legs of the triangle have been sort of pushed apart farther in order to accommodate a side of 14. So this means we're dealing with an obtuse triangle here. And that would be our solution to this problem. We have an obtuse triangle. So the Pythagorean theorem, super famous, super useful. And that's a great place to stop right there.